Hello, everyone. We're going to start. Thank you. So today we have the pleasure to have Roberto to present his work. So he's part of the data lab here at Medea and also a PhD student working on machine learning, AI, big data. And so today he will present part of his work.
Thank you. Hi, everyone, and thank you for coming. Welcome to a new seminar here at Medea. For those who don't know me, I'm Roberto Alcaraz. I'm working at the data lab. Also, I'm doing my PhD in AI applied to environmental systems. And today, I'm going to talk about my last work, which is ReMatch, a new AI algorithm for wildlife identifications by matching key points and lines. This work has been a collaboration with the animal demography and animal ecology and demography unit, and also with the help of my supervisors, Angela Mores and Marta Arcos. So let's start from the beginning. I'm going to introduce you the start of this study, which is the Balearic wall lizard. This is an endemic species here in the Balearic Island, but well, not really. It's an endangered species. Now we cannot find them in Mallorca, neither Menorca. We can find them in a small island like Sa Dragonera or Menorca, or a small island around Mallorca. So, as I said, the Animal Ecology and Demography Unit has been following them for more than 15 years in all of this island to study more their dynamics. So they wanted to ask some of these questions, like to estimate the population, the survival rate, or the fertility of the population. And to study all of these things, they need to analyze individual-based data. Okay, they need to have data from each individual. But how can we do that? Here we can observe a normal image from a day of work, where here in the chest, the lizard have a escape pattern that is unique for each of them. Here we can see it better. It's a scale pattern that it works like the human fingerprint. So it is unique it's a distinctive pattern for each of them, and it allows us to re-identify after another capture. So what's the challenge here? So the challenge is to re-identify the same individual across multiple captures. For example, here we have 3 images, one from 2009, one for 2011, and another one from 2012. We need to find a way, an algorithm that after many captures, the algorithm have to be able to re-identify and say, okay, these 3 images belong to the same individual. And indeed, they were already doing that. AFIS was a software tool for photo matching that was presented 10 years ago, in 2015. And this is how it worked. They had the pattern, and the person had to mark each of these points for a new image, and it was compared with all the images in the database. Then we had an error metric with all of them, and we ranked them for the, I don't know, I think the 50 or 100 possible candidates with the lowest error. However, AFIS has some limitations. The first one is the heavy manual processing, because all of these points have to be marked by a human. So at the end, it's a tedious process and it's very time consuming. Also, it leads to human errors and limitations, because a person can to annotate all these images. It takes too many hours, and you always have some errors here. And also another important thing is that it doesn't have open set capability. When we say open set capability is when an algorithm has this open set capability is that it is able to identify new individuals. Okay, because they were given a list of the top 100, but it wasn't, if a lizard is new, it wasn't able to say, okay, this is new. So one day, Andreu, that is not here, come to my office and told me about this problem, and we say, okay, let's try to make something automatic to this problem. So that's how ReMatch was born, which is re-identification of pattern species like the Balearic word lizard in open set scenarios, that is capable of detecting new individuals by matching key points and lines. This is the paper is under revision, and if you want to look at it, the preprint is available online. So let's start by looking a little at the methodology. So the thing is, we will have all of these images in the left. After some preprocessing, we get like black and white scanned images, and then we apply the image matching algorithm to extract points and lines and compare them. For instance, these two images belong to the same individual, and because of that, they have many points in common and many lines in common. So this is the pipeline. This is the steps we follow in all this process. These are mainly four. The first one is to prepare the images. Then we match all the images on the database together. After that, we aggregate this feature. We aggregate the statistics we obtained from the step before. And finally, we train the model first. And then with new images, we apply the model we have trained before. So we will start with the first one, which is the most important part in this project, which is the image preparation. First of all, we have these raw images. When some of them are from more closer to the lizard, others don't. We have shadows, different qualities. So there are too much noise, so we have to isolate the body. To do that, we are going to use two AI models. One is the grounded SAM, which is a combination of two foundational models, grounded Dino and the segmented model. And as you can see in the image, it allows you with a text prompt like ChatGPT, it allows you to segment whatever you say. For instance, in this image, you can say horse, and it will detect and segment all the horses in the image. So it is a very good tool because we can try to extract automatically mask of the body, and then because we will have good segmentation mask and bad segmentation mask, we will train with the good one JLV8 segmentation model with a good annotation. In that way, we will have a good segmentation model that will extract the model. In this case, the prompt we used was this one, the top part of the chest without head and arms. We combine these two, and we get these two. Well, for every image, we get the body segment. Okay. However, it is still not very clear because the important part, as we saw before, is in the upper part, because the rest is not so important. So we have to extract the scale part. And to do so, again, we will use the segment anything model we were saying before, because it allows you to segment, as the model say, everything. So in our case, it's very useful to detect the scales. Okay. So we apply it and we get these black and white images for all the images in the database. So at the end, we have the results in the paper are with Kurt, which is a small island in the south of Mallorca. And at the end, we have more than 4,000 images from 1,000 individuals, because it's like more or less 4 images by individual. So it's a very low quantity. And that's why this re-identification problem is so difficult. Now we move to the second part, which is the pattern matching. And here we will use another, the BlueSteel, which is an image matching AI model that allows us to extract points and lines from 2 images and compare them to extract common points and lines. So what we have to do now is to compare all the images in the database, all the images we had. We have to compare all of them to have some statistics. And we can have two cases when 2 images belong to different individuals. For example, here there are a few points and also few lines in common, because as you can observe, the pattern is different. However, when 2 images belong to the same individual, we can have many more points and many more lines. So this was very interesting, because we can differentiate the same pair individuals against the different pairs. Then we have to aggregate these features in order to train a model. So we will extract 4 features from the results we have seen above, which are the match key point, the mean key point probability, because each match key point has a probability. So we obtain the mean key point probability and also the match lines and their corresponding probability. For instance, the previous example, we have like more than 500 key points with 0.68 of probability and 175 lines with 0.72 of probability. So these are very high values. Here are the distributions or the considered variables. As you can observe, they almost split the data into same individuals are different individuals. So it indicates that the image matching model is working very well, and we can almost split the data in these 2. So knowing that, we are going to train the model. The goal here is to predict if 2 images belong to the same individual, to the same results. So we will have the 4th predictor we have said before, and a response binary variable, which is if they belong to the same individual or not. We will split the data 70% for training and the rest for testing, and we will test 3 machine learning models, which are the random forest, XGBoost, and CatBoost. And we select the one with the best F1 score, because it's a very good metric to deal with imbalanced data set. However, single images can be misleading, because depending on the quality of the images or bad angles, we can have low probability even if both images belong to the same individual. So to fix that, the solution is to aggregate the probabilities by each ID candidate. So now we change for each new image, instead of having a probability a probability with each image of the database, we will get a new probability for each candidate. So it's better, because now bad images were are not going to be such important. And this solution makes us have the OpenSec detection. That is, it allows us that when we fix a threshold, if that probability is below the threshold, we will identify it as a new individual, and when otherwise it is above the threshold, we will match it to the best candidate. Okay, so now we move on to the part when we have a new set of images. So the steps are more or less the same. These 4 steps, the image preparation, pattern matching, feature aggregation. But then the last one is to apply the model we have trained before. So for a new set of images, we will have to prepare, match, score, and decide. So as we have done before, we process from raw images to processed images. Then we match all the new images versus all the images in the database, and we will have a table like this. On the first column are the new images, the second are the images in the database, and there the 4 features between them. Then we pass this data set through the model, and we obtain a score. Here we have the best candidate for each new image. The best candidate is the ID with the highest probability. Okay, so here we have for each image predicted ID with a probability. So with the threshold we have defined before, if the probability is below that threshold, we will consider it as a new individual, for example, here in this case. Or if it's above this threshold, we will identify it as a recapture. After that, we give these results to an expert, and he has to decide if the results are too low. It could happen that, for example, in the second case, even though the probability is high, maybe it is not that individual, and maybe we can consider a new individual. When everything is reviewed by the expert, now that we add these new images to the database to be able to process again another new day of fieldwork. Okay, so now I'm going to show you a little experiments and result we have done, because, well, this model seems to work very well with lizard, but how does it work with other species? So we have tried it with other data sets, with zebras, with seals, with whale sharks, and with human fingerprints. And we have tested in 2 scenarios, in the closed set scenario and the open set scenario. When we talk about closed sets, is that all IDs from the test set are in the training set. That's it. All the individuals in the test have been seen before. We tried this scenario because the majority of re-identification models do not have the open set capability, so they work as in closed sets. So we compared us against the mega descriptor. The mega descriptor is a foundational model presented in the paper wildlife dataset that is right now the best model in re-identification. So it worked in closed set results, so we compared our model against it. We can observe here the results. The mega descriptor is better in the whale sharks and in the seals because it has like different viewpoints, and for our model is sometimes complicated to detect. But when we have patterns, that is in the lizards, in the zebras, or in the fingerprints, our model is outperforms the Balearic script by far. Also, we can see our results in an open-set scenario. That's it. Our model can detect new individuals. So these are the results for example, for the lizard, it currently identified around 93%. Also, another interesting result that I wanted to comment is that that ReMatch was highly effective at detecting annotated errors in database. What does annotation error means? Is that we have two individuals categorized as different when they are the same individual. So, as an example, here we have two islands from Mallorca, Curt and Montona, when they get these images. And this is the mistake we have solved, like almost at 10% for Curt and almost 5% for Montana. Also, for the public data sets of the zebras and the seals, I found also mistakes in the data I have communicated to them. So finally, as a conclusion, first of all, is that the re-identification pipeline has an open-set detection, which is very important because at the end, the environment is not fixed, is not closed. So it's important for an algorithm to detect a new one. And not all model has this, so it's a very important advance. Then, as we have seen in the results, it has a great recognition accuracy when dealing with complex pattern. Meral descriptor was like 80% of accuracy in top one with the lizard, for example, and ours more than 90%. So we can see that it works very well with pattern and also with human fingerprints. And finally, the robustness of our pipeline along different species. That the algorithm not only works very well with the lizard, he can do it with many more species. For example, here in the two images above, we have the whale sharks and the zebras we have worked, but below we have the groupers. We make a trial, and we saw that it can be used to identify them, and also in sea turtles, and I also tried with frogs, with another salamander, and it worked with many different species. So that's everything. But before going, there is a bonus track with two presents. The first one is that I could have done that because I have the capability of doing that, because here we have some machines that are very powerful, and without them I couldn't have them. So if you have read the newsletter, but maybe not, we have a new workshop in November. In a month, we have do a workshop to get started with the UIB-CSIC servers. This is the first one. This is perfect to learn how to enter to remote servers. And then we are preparing another deep learning 3-day workshop held by the Computer Vision and Behavior Analysis Lab from la Universidad Politécnica de Valencia. They are going to come here in January, and you will have more info coming soon. So that's all. Thank you.
So you think is less robust? Identify the species doing you have less point connection or less lines compared to zebras or tortoises against whales. I don't know if this is because whale has a lot of points
Yeah,
and the others have less points. Maybe that is why it's less robust, identifying this species with a lot of lines with points.
yeah, and the species with more lines, because as in the whale sharks, you don't have any line, you only have the spots. So that's why the algorithm is not so reliable in this thing. But yeah, if you have also lines, but in the case of the zebras, or I don't know, maybe another, for example, in the groupers, you have some points that are bigger, and maybe you can detect some lines. So it works like it works very well with the points, but if you also add the lines, it will work much better. Yes. Yeah.
Thank you for this very cool presentation, also very concrete to your great algorithm. I have one question: how much does the angle of the photo influence the result? Because for the lizard you get a nice front photo, so there is no tilting much. But maybe for these big animals that you cannot just capture them and photo them from the front, you might have an angle.
Yeah, this is a very problematic thing we have found. Well, the model that identifies the matches only works with rotation around I don't know if 30 or 45 degrees. So it's not like if, for instance, we have also I haven't said here, but for the lizard we also change a little the rotation, because if a lizard is like this and the other one is like this, they have an angle of 90 degrees and you cannot find anything. So we have to rotate all of them to have like a 0 degree. Okay. And that's why also in the whale sharks is not so good, because you have different viewpoints from on the top, on the bottom, and it's very when it has a rotation more than 45 degrees, it cannot detect anything. So it is one of the drawbacks of this algorithm. But for instance, in the zebras, here the rotation is not so important because they are always in the or one side or another. But in the groupers, more or less, well, in the groupers there are more rotation. But yeah, the rotation is an important challenge.
Maybe there's a machine learning algorithm for rotation, I guess.
I tried that.
Okay.
But it's yeah, we tried many things, but at the end we fixed one. But that's it. And other thing is that well, the problematic thing is for instance for the lizard, because all the images are like vertical, but the rotation can be very big. But with other, if you have, for example, rotated images like one like here or one like this, you cannot find them. So that's why it's very important the image preparation step. Yes.
Thank you very much for your presentation and for your incredible work. When we began this project 15 years ago, people chopped finger for the recognized laser. And we didn't want to do that, of course, but we didn't know how to do it. And 15 years after, knowing that you have a fast and non-invasive way to recognize thousands of icons, that's really fantastic. I was just wondering, just a curiosity, your algorithm works better in human fingerprints than the Mega or whatever you call it. So which software, well, which algorithm they use actually when it's important to find a correct fingerprint?
Well, also the fingerprint is, we have very few images, like, I don't know, they were like 800 images on 80 individuals, or so that's why the algorithm works pretty well. But if you ask me for the rate, then for the algorithm in fingerprints, I don't know the FBI ones. Maybe I can sell it.
Yes. Right.
Yes. The one.
So thanks for saying it was really beautiful. So sometimes in order to train, if you have sort of like a physical model or a model of the physics of this, for example, of the object that you want to recognize the pattern or whatever. So you can generate data based on this physical model, meaning data that is plausible, right? And then this generated data can be used to train the algorithm. And this in general works quite well, at least the cases that I know. So I was wondering whether, my understanding is that one of your problems is that you have, for example, a small number of pictures of each individual, but you have a lot of pictures overall. So I was wondering whether it would be possible to sort of learn the general structure, right, of this data in order to produce synthetically data for different individuals, and then morph these, because basically what you have is a conformal mapping of one to the other, one picture to the other picture. And then use those to train the algorithm.
Yeah, it would be nice. That's a very interesting point. The problem also here is the matching part. And the more images you have, the more time you get, because here we have around 5,000 images. So for 5,000 images using GPU acceleration is more or less 3.5 days or 4 days, because you have to compare each with each of them, which at the end are 10 million pairs. So if you increase this number, right now I'm trying the model with sea turtle, which have like 8,000 or 9,000 images, and it is going to last 15 days. So this is like yeah.
So now I was thinking, if you, for example, sometimes you don't need to, so if you could categorize your data based on big scores, right? So gross level of score. So then you can say this is more like that or that or that. So then you only go afterwards and score within a subgroup.
Yeah.
Right, and that would accelerate quite a lot.
Maybe that's some point. Thank you.
So, you talked about setting up threshold value somewhere in efficient reason. Threshold value,
Yeah.
like how do you decide, on what basis do you decide that value?
The threshold.
Yes.
Because of the F1 metric. The F1 metric is a very useful technique when you have imbalanced data, which is our case. It's imbalanced because the most probable is that the two images belong to different individuals. So we have like, I don't know, I think it's 0.005% of the rows are from the same individual. So the F1 score penalizes more the true negatives. The false negative than the false positive. So if you find the threshold that has the highest value of this metric, you take this value. We try for it with a lot of thresholds, and the one with the best value, you get.
Yeah, I was wondering about the aggregators that you were talking about. So you have the whole data and then you choose some kind of not a proxy, but like an observable of your data that you will use then to know if the two patterns match essentially. I was wondering why you use this for aggregators and why not, for example, like another metric to compare different networks in that case.
Well, I don't know if I understand your question. I use when the glue stick, which gives you is like a vector of descriptors of the images. So these vectors that are really, really big, I aggregate them. Well, I get summary statistics of I reduce it to the number of points, for example, instead of having a long vector of 1,000, I reduce it to only a number because I saw that it is enough to split the data. Before I thought about doing that, but it is not necessary because only with these 4 variables, it explains all the data.
Maybe one last easy question. Me as a potential user, how I can access your code and apply it to my data?
Interesting question. Well, this model is already being used for the lizards. Well, now we don't have a tool to use it. So they pass me the images, I process them, and I give it back. But when the paper is published, we are going to publish also the code. At the end, it's automatic. So you have to get your images structured in some way, and then you pass it through the model, and it generates everything.
Yeah, super interesting talk. Thank you. And yeah, my question is because you say that it takes very long to train, but I guess that you only need to train it in the beginning, and then you can re-identify the images without training. Do you need to train? I mean, is it good to train again once you get more images? Or
I think it's not needed because the training is with the training part is with the pairs. So you have millions of pairs. So
and then how fast is it to apply it to a single image?
As I was telling to Martin, the most time consuming part is the matching part. So if you have, for instance, 20 images, 20 new images, and in the database there are 5,000, you will have to do like 100,000 comparisons, and maybe in some hours, in 2-3 hours, you have. But if you have many more images, so if you do it by small batches, like 30 or 50, maybe in 2 hours you have.
Yeah, let's tell us how many time we invest before for processing each image. Because it seems that it's a lot with the but it's nothing compared with no?
Probably 4 days for 100 individuals.
And also at the end, you need also this final check by a researcher, like checking that or at the end you can rely on what
I think what you should do is to check at the end. But for instance, if you have like a very low probability, you can have, or for example, for the lizards, if you have a very low probability, or you have a new individual, or the image is bad. Because maybe since the image is bad, they have the comparisons have been worse. So, but if the image is well, it's like the images is like the one I told you before, and the probability is low, it will be a new individual. Because the probabilities are very different. Like, well, if it find a match in the database, maybe the probability is 0.95, 0.90, maybe very high, and if not, it's 0.000.
And you don't have programs with similar individuals? Individuals that have similar probability? Very, very close, and you have to decide. There's a way to identify that maybe there are two lizards that are quite similar.
This is less work. Yeah, because I talked before about the similar lizards. That is because when we first trained the model, I find like images from different lizards that have many points in common with a very high probability. And then I checked, and I'm not an expert in lizard, well, now probably yes, but I said, okay, this is the same. And I passed Alex like 100, 400 or 500 pairs to check. Here, thanks to that, we have fixed a lot the database. And there are also cases when I don't know if they are similar or not. Then I have to tell you about one that I think they are cousins. Or something like that.
Thermogenesis.
Okay, so we can leave it here. Thank you very much.